In this tutorial, we will discuss interfacing EEPROM with 8051. Now, you could have come across situations where you wanted to store some of the data permanently on the microcontroller. Like say for instance, you are reading sensors and you want to store the sensor values, and even if the board is turned off and turned on again, you want to retrieve back those values. In such cases, EEPROM comes in handy, and in 8051 we do not have an inbuilt EEPROM memory. So in this tutorial we will talk about interfacing the AT series. It's from AT24C16 EEPROM. So this tutorial will also be good if you're using 2408, 04, 02 or 01 series of EEPROMs from Atmel. Now this tutorial, it uses the I2C.C functions which we have discussed in the I2C basics video. You could also watch the RTC tutorial, which again uses the I2C functions, and then we read and write time from the RTC IC. So it is highly recommended that you go through these before you go ahead with this tutorial. And if you are following along these tutorials in a series, you would by now be familiar with I2C start condition, the stop condition, then the device IDs that are used in I2C, and also positive negative acknowledgement. And in this tutorial we will not talk about I2C. We will go ahead and speak about the interfacing AT24C16 EEPROM. Now the 16 in the IC number, it stands for 16 kilobits of it's not kilobytes, it's just 16 kilobits of EEPROM. Alright, so these 16 kilobits, these are arranged, the memories, if I could draw the memory structure, these are arranged in chunks of 8 bits, or in other words, this is bit addressable. So each location in the memory is 8 bits. Alright, so now since there are a total of 16 kilobits, which is 16 into 1024 bits, this it has, since these will be 16 kilobytes, it will be total 16 into 1024 bits, and these are arranged as 8 bits per location. So the number of locations we have will be 2 into 1024, which is 2048. So if I start from 0, the last location would be 2048 in decimal. Now this is important, and we'll discuss as to what the differences are in these memories. Now let us go ahead and see that. Now before you go ahead and see all of that, this is a very tiny 8-pin IC, and what you could see is there are 2 pins for power, 4 and 8, and then 3 lines. Now these are the address lines. Now this address, it does not mean a typical address. What it means is on an I2C bus you can connect 8 such devices. Now we'll see how we can connect those, and so these are the 3 pins. So we have 8 combinations of these, and then we have the I2C lines SCL and SDA. There is one more pin called the write protect pin, which is used to protect the IC from being written. Now we'll discuss the address lines in a little detail now. So before we go ahead and do that, we'll have to continue our discussion on the memory arrangement or the memory addressing. Now what we have is for let us start with the 2401. So this is the IC number. So this is AT24C16. Now this has memory of 1 kilobits. Now this is all in bits, not in bytes. So this 1 kilobits, to address 1 kilobits of memory, so these are arranged in 8-bit chunks. So we have in total 1024 bits, and these are arranged as 8 bits, as 8 bits per location. So that would be 128. Now if I write the number of bytes this memory has, this would be 128 bytes. So it's pretty small. We can just store 128 bytes into this. Now the next in the series is AT24C02. Now this has 2 kilobits, or if we again divide this by 8, we will have 256 bytes. And the next in the series is AT24C02. In total it has 4. This would be 4. So this has 4 kilobits, and this would be 512 bytes. Now similarly we have AT24C08. This is 8 kilobits, and that would be total of 1024 bytes. Similarly we have the AT24C16, and this addresses 16 kilobits, which is nothing but 2048 bytes. Now so the 24, now what we will be discussing in this video is AT24C16, and this has 2048 bytes of memory. Alright, now here is an important point. On a I2C, on a normal I2C protocol, what we have is we have a 7-bit address, right? So, and of these 7 bits, 4 bits are fixed. For this IC, those 4 bits are 1010 for any of these ICs. Now what are the next 3 bits? So the next 3 bits are A0, A1 and A2, and the last bit is read/write bar. If you want to read into the device, you want to write into it. So this is in total the 7-bit address. Now if you look at the AT24C01, so all these 3 bits are used normally. So what it means is we can connect up to 8 such ICs on the bus, and then we can have all of them connected, and we can read or write into them. So only thing we need to change is we need to change these addresses, and these pins need to be connected as to whatever address we mean. So what I mean by that is, like say these 3 bits are 000, then this points to the first IC. If it is 001, then it points to the second IC. So this pin needs to be connected to VCC for the second IC, and these two need to be connected to ground. Now here is an important point. So in effect we can connect 8 such ICs, and the total memory that we'll get out of that will be 8 kilobits, right? If we connect all the 8 ICs. Now if we connect, what happens next is for the AT24C02, again we can use all of the 3 address lines, and we can connect 8 such ICs. So if you do that, then also we will have this 2 kilobits into 8, which is 16 kilobits. Now Similarly, now what happens to the next IC is, instead of using the 3 address bits, what we have is, this will be divided into pages, and what we will have is only A0 and A1. So instead of A2 we will have the page 0. Now what that means is, you can connect only 4 of these two make a combination of 4, and then we can connect only 2 such ICs, 4 such ICs, and 4 into 4K it makes 16 kilobits. And for the next AT24C16 this we cannot use this will be used for page addressing, and we can use only A0. It means A0 can be only 0 or 1, and we can connect only 2 such ICs. So for the 8K we will have 2 ICs which will make 16 kilobits, and for the, when you are using AT16, it does not matter if you have connected these, because all the 3 bits in the addresses will be used for paging, and this would be read write. Now the point here is, so instead of connecting 8 of these, or 8 of these, or 4 of these and 2 of these, or what you could do is, if you want 16 kilobits, you can directly go for AT24C16. And in our example, what we have done is, we have connected all these 3 pins to ground. So no matter what IC you use, the address would remain same, and we ensure that at any, we will use only one of any of these ICs. So now we'll discuss this paging in a little more detail here. Now for this IC, for instance, for the AT2416, what happens is, these 3 bits, which is 2 to the power 3, these make 8 pages, and one page it can address up to 256 bytes or 2 kilobits. So let's say it's 2 kilobits, so that would make into 2K, which would be 16 kilobits for this. Alright, so let us see that in a little more detail here. So the memory map for the AT24C16, it would be something like this. This is page 1, this is page 2, this is page 3. Similarly, we should have page 4, page 5, page 6, 7 and 8. So this, for instance, it's page 8. So this is page 1, page 2, page 3, and we have page 8. Now the addressing for this would be, so what addressing we need to follow is, say we want to address page 1, or rather we'll start it with 0. So this is page 0, 1, 2 and 3. Now if you want to address page 0, when we need to select the device ID, or when we send device ID over I2C bus, the device ID would be 1010. This is fixed for the entire series, and then the next 3 bits would be the page number. So for the first page it would be 000, and the next bit would determine whether we want to read from memory or we want to write into it. So this is read/write. Now these 3 combinations, these 3 bits will give us 2 to the power 3, which is 8, so we can access 0 to 7 pages on the memory. Now if we do that, we have already seen that since this I2C will be configured to transmit 8 bits, per transaction, or we send a packet of 8 bits. What we do is we send the device ID, and then see we want to read from the memory, or say we want to write. So what we do is, so if you want to write in this case, so this bit would be 1, since it's read/write bar. So we send the device ID, we send the page number, and we send that we want to write. The next what we need to do is we next need to send the address where we want to write. Now this in total, now since this is a total of 16K, now each page, as discussed earlier, it is of 2 kilobits, and these 2 kilobits are arranged in chunk of 8 bits. So the first byte, the address of the first byte would be 0x00, and the address of the last byte in this would be 0xFF, or 255 in decimal. So this is total of 2K. So we have 8 2K pages, which makes 16 kilobits of memory, and each page has 255 bytes, or 2 kilobits. Now, so what we do is, first we send the device ID in this format. So to access page 0, these 3 bits would be 0, and then we send the location on which we want to write. Now say I want to write on the first location, so I would send all zeros, and this would be all this. These 8 bits in every transaction would be followed by an acknowledgement. So this is the basics of it. So say if I want to access the page 3, then the page 7, then all these 3 bits would be 1. So this would be the address that I would be sending. Now what we do in this example is, we would go ahead and store 8 strings on starting location of the 8 pages. So we'll store the 8 strings, and then we will retrieve them and display it on an LCD. Let us go ahead and look at the schematic that we'll be using. Now as you could see here, the connections are very simple. We have connected the A1, A0, A1 and A2 address lines to ground, because you're using only one of the IC. So we are using only one on the bus, and the SL is connected to port 3.6, and SDI is connected to port 3.7. We also have an LCD which displays all the messages, and this is connected in 4-bit mode to port 1. So if you watch the LCD tutorial, so this should be pretty familiar with it now. So since the connections are very simple, let's go ahead and look at the code now. Now again, I recommend you to go through the I2C basics video before you go ahead with this. Now so the functions, so this is EEPROM.h file. This file has all the functions to access the EEPROM, read, write and all of that. So now let us look at the first function. So what it does is it writes a byte into an EEPROM. So what we give is, we give a EEPROM address, then we give the data that we want to write, and then we give the page number. So the page number in this case would be 0 to 7, and similarly there is a function to write n number of bytes, right? So we can consecutively write n number of bytes, and to do that we have again the same, we give the EEPROM address, and then we give the RAM address from where you want to write those bytes, and then we give the number of bytes that we want to write, and then we give the page number. So similarly we have a function to read from an EEPROM, so a read byte. So again it gives the EEPROM address, then and it gives the page number. and the function returns the data that is read. So similarly, we have functions to read n bytes, write a string, and read a string from EEPROM. Also, there is a function to erase the EEPROM. Now let us go ahead and look at the individual functions. Now the first up is the EEPROM write byte. So that is what we logically do before using an EEPROM. So we write to it first. Now you could see that the EEPROM ID is defined as A0. So this is fixed, and as discussed earlier, it would be 1010. Now what you could see here is we're using functions from I2C.h. So we'll be using all low level I2C functions and the delay as well. So the ID is fixed. Then what we do is, now if you could see, look at the timing diagram here. First we need to send the I2C start condition, and hence we send that. Then what we do is, these next 8 bits would be the address, the device address. And in our case, what we have is the EEPROM ID is 1010, and now as discussed earlier, so this would be the page numbers P3, P2, P1. So these bits would be page numbers, and the next two would be a read or write. And in this case, since we are writing, so the read/write bar, since we are writing, this bit would become 0. Now what we only need to do is to provide the page number, and this page number, since the page number is between 0 to 7, so what we have is, say for instance, page 1. Say we want to write to page 1. Now since this bit, so only these 3 would be important to us, because the maximum page number would be 0, 1, 1, 1. So this is 7 in hex. So what we need to do is, these 3 bits, they need to fit in here. So what we do is, we shift this one time towards left. So say for 1, for instance, so if we shift it 1 towards left, so what we get is this. And then what we do is, we OR it with this particular value. So when we OR it, what we get in effect is the EEPROM ID with the page number. So for this instance, it would be page 1, and this would be a write operation. So this is what is done with this instruction. And as soon as we do that, so you can see that this is 1010, and this is the page number. So for page 1, it would be 001, and then whether we want to read or write. So if you want to write, then this bit would be 0, as shown here. Now as soon as we do that, we need to send an acknowledgement. So we do I2C ACK. Then what we do is, we write the EEPROM address. So the total of, we have 0 to 255 addresses, so any of which is given will be written. So we take also EEPROM address here. So the same EEPROM address is wrote on the I2C bus. Then again we send an acknowledgement, as you see here, and then we write the exact data. Then again we have an acknowledgement, and then we stop the communication. Now if you go to the data sheet, what you could observe is, it takes about 5 milliseconds for the EEPROM IC to write the contents of EEPROM internally. So once we send a byte into it, it takes about 5 milliseconds for it to write it to the memory, to its internal memory. So then similarly, the next function is to read byte from the memory. Now what you could see is, the first difference would be, instead of the read write bit being 0, we make it 1. So not here. So before you go ahead and read from the EEPROM, we need to make a dummy write, right? And to make a dummy write, what we need to do is, we start the I2C as here. So we start the I2C, we send the EEPROM address and the page number that we want to access, and then we say we want to we send an acknowledgement, and we say we want to write, and then we send an acknowledgement as shown here. Then we give the address from which we want to read. So before we read anything, we need to write the address first. That is why this write operation is done, and then we send the address from which we want to read. So the EEPROM address, it is written onto the bus, and then you acknowledge, then we acknowledge the communication, and then next we start a fresh transaction again. Now this time when we give the device address, we would in fact be reading the data from the memory. So that's what we do. We start the communication, and in this case you could see we used A1. So what A1 does is, this is 1010, then this is P2, P1 and P0 for the pages, and if this bit is 1, so it means we are reading from the EEPROM, and then we again OR the page number as discussed earlier, and then we send an acknowledgement. So next 8 bytes what we get from the bus is the data. So, and then we stop, and it again takes some time to retrieve, and then we return the byte which is received here. So this character, it will read a byte and then it will give it back to the calling function. So similarly we have functions to write n bytes and read n bytes. So what they do is, these functions, they use the EEPROM write byte and read byte functions, which are used to write and read single bytes. So n bytes, it simply uses the function n number of times. Similarly we have functions to store a string. So now the only difference between writing n bytes and writing a string is the string should be null terminated. So if we write ASCII values, we should know when we go ahead and read those from the memory, it should be terminated with an ASCII value. So so that is what is done, and we increment source address and the EEPROM address, and we again use the EEPROM write functions, and we use this till we encounter a null on the string. Similarly we read a string. Similarly we use the EEPROM read string function, and in this we read till a null is found. So these are pretty simple functions again. Let us go ahead and see how we could write into all the 8 pages and read it back. Now this is the main program, and we've included all the files that we have discussed. We've included the EEPROM.h, and this has I2C.h and all the relevant functions. Now this does not matter, so this line does not matter, so we're not using it. Now we initialize the LCD, we go to line 1, and then we display some string, say AT24C16, and then what we do here is we call the EEPROM write string function, and what we pass is the EEPROM address, which is defined as 00 in this case. Okay, so we are writing at starting of each page. So we have 8 pages in total, and we will be writing at starting of each page. So what we do is we send the string as P0 hello, and then we write it on page 0. Similarly we write hi on page 1, good on page 2, morning on page 3, how on page 4, is on page 5, year on page 6, and day on page 7. And what we do here is we read back from the memory, and then we display it on line 2. So we go to line 2, we just clear if there is anything already existing on the LCD, otherwise it would overwrite. Then we go to line 2 again, and then we write it as RD, what is written from the EEPROM, and then we actually go ahead and read the EEPROM. And since this loop is going for 8 times and the EEPROM address is 00, it would read back all the strings that we have stored. So this count would go from 0 to 7, and in the meantime it would read all the strings from the EEPROM, and it would store in the read string a read string array, and what we do is we display this read string on the LCD. So what we get with this is this is a very dummy program. So what you basically get is you write into memory and read it back. So to actually test it, what you need to do is you need to write this entire function first, and then what you need to do is you need to comment from this point till this point, and then you need to write this again into the controller. Now what that would do is for the first time when you write, it would store all of this into the memory, and then when you write it for the second time, what it does is it just reads directly from the EEPROM. So and to test, what you could do is you can turn off the board, remove the power, connect it back, and run the program. So it would still retrieve the data, and it would still store it. Okay. So watch the demo, and thank you for watching.